Okay, students, good morning. So, the last class, okay. Yesterday's last class, we were discussing regarding the principles of achieving mainly the accuracies and various examples and the measurements. Mainly, it's related to accuracies, always mainly related to the measurement and the precision, everything we were discussing. So, we were telling an examples and we were just telling about surface roughness. In surface roughness we are using grinding tools, and what is the purpose of grinding tools, then what are the requirements of a grinding tool, then how do you measure the precision and accuracy of a grinding tool. In the grinding tool it was mainly regarding the grinding wheel, everything. Okay, so now today we are going to discuss about, okay, in this module, so the first we are discussing about metrology, then we were discussing about the measurements, the various types of measurements and instruments, then we were discussing about the accuracy rate, precision, everything. Then we comes to tolerances and allowances. Okay, tolerances and allowances, you might have heard this word tolerance and allowance everywhere, but as per the mechanical point of view it comes in a very important role, as it is the maximum limit. Okay, it is the limit, the range of the variation permitted in a specified dimension in a machine piece. That is, it is always the range that if we have a dimension, the dimension can exceed to certain extent in order to complete the process, or in order for achieving it might not cause any issue in the process or any issue in the attachment or something like that, we can say. So that is what we can say in a small definition of tolerance. That is the allowable deviation from a standard deviation. Okay, that is, that's a standard. Like for example, we have a laptop that is having we are manufacturing a keyboard on it, where the keyboard specification for a 15-inch laptop is, for example, we can say 32 centimeter. But there is an allowable deviation available with respect to example. That is, if you have a 32 centimeter keyboard, we can make it to 32.2 or maximum 32.0102 to 32.2. So that is the allowable deviation. So if it happens also, it will serve the purpose without any much issues or any much criteria. That's what we can say in the case of tolerance. So this I have set an example. Okay. So in the case of tolerance, that is the allowable deviation from a standard. Okay, that's the allowable deviation from a standard. And in single word, we can say it is the allowable deviation from a standard. Example, the range of variations permitted in maintaining a specified dimension in a machined piece. That's what we say. The allowable deviation is a standard where the range of variation, it is mainly the varieties of ranges of variation permitted in maintaining a specified dimension, so that it might not affect any functionality or any ability or any issue regarding the process for what it is been required, okay, in a machine service. This is what say. So I can show you a small figure. You can see the small figure where you see this is the upper limit of, this is the maximum, the upper limit. Okay, this is the maximum deviation and this is the lower limit. So this is the, so here we have a tolerance where anywhere inside this will be applicable for the purpose. If so, anywhere inside this can be applicable for the purpose. I hope so. You are carrying your notebook, so just draw the figure and just measure, just mark all this: the tolerance, the lower limit, and the upper limit. This is the basic representation of figure of tolerance. So upper limit is the maximum limit and lower limit is the minimum limit. Other than this, if it exceeds the upper limit, it is not suitable, and if it decreases or descends or exceeds the lower limit, it is not suitable. So the difference between the upper limit and the lower limit, that small difference, that's called tolerance. That's allowable deviation, which will be applicable for the purpose. This is what happens. So one word we can say, the allowable deviation from a standard. Now we can just have a brief discussion about the tolerances, the main definition, everything, where we have tolerances, where that is, one second. See, these are the tolerance. Okay, these are the main aspects of tolerances, like the allowable deviation from a standard, which I have discussed now, the allowable deviation from standard. Like, then we have a small, what are the factors affecting the tolerance, we can say. Tolerance is the total amount of dimensions which may vary and is the difference between the upper and the lower minimum limits. For that only, I told you to draw the figure. Hope so you have drawn. Rahul Rajiv, have you drawn the figure, or should I share this figure screen again?
Yes, sir.
You have drawn the
Yes.
figure. Fine. Okay. I'll just share one more time. If anyone has not drawn, just note it down. Okay. This is the figure which I'm telling about in the case of tolerance. It's just a very simple figure. You see, simple, the tolerance is mentioned. You have to just mention this key terms, that is tolerance, lower limit, and upper limit. And in one word, you can say the allowable deviation from a standard. That's what we say. So the allowable deviation from a standard. Now, in the case of tolerance, it is the total amount of dimensions which may vary. It may vary. It is not compulsory. It should vary, but in most of the cases, there could be human error or due to some other error, it may vary. Okay, and is the difference between the upper maximum and the lower minimum limits. Okay, and is the difference between the upper maximum and the lower minimum limits. Then regarding the types of tolerances, it is two. That is both, one is dimensional and second one is geometrical. Okay, one is the types of tolerance, the two types mainly we are discussing. That is one is dimensional and other one is geometrical. That's what we say. Then in the case of tolerance, we always have an allowance for a specific variation in the size of part is called dimensional tolerance. So there is an allowance, we have given an allowance as a small span or small time period. Okay, that allowance, that's called allowance, which is allowance for a specific variation in the size of a part is called dimensional tolerance. Okay, allowance for a specific variation in the size of a part, it is mainly called a dimensional tolerance. And allowance for a specific variation in the geometry of the part is called geometrical tolerance. So this is the types of tolerance where we have two cases. One is dimensional tolerance, and the other one is geometrical tolerance. In the case of dimensional tolerance, it is the allowance for specific value in the size of the part. This is the factor, the change in both dimensional and geometrical. The changes in the word is it is one is the in the size of the part, and other one is in the geometry of the part. And both will be having an allowance for a specific variation. It will be not very huge. It is like at the time of machining or at the time of producing or at the time of manufacturing various products, what happens? Always there will be small errors which cannot be identified with human or naked or with any instruments. But when compared to humans, the instruments are more precise. Like I told in the last class during the measurements, like in the case of vernier caliper, everything, we can have a measurement very close to the precision, that is 0.01 or 0.02 also. So all this comes into case of the tolerance and allowances, where we can have a specific variation. Make it in the exact way, it might affect the, it not might, it always affect the fit and finish. And due to climatic condition and expansions or some other small soil heating condition or some expansion or contraction takes in place, it will become unsuitable for the purpose. So in order to avoid that, we always keep a small tolerance, allowable tolerance of space. Like even if you can see in the case, even there is a building constructions also, if you are making a huge building, there will be a small tolerance you can see in the buildings. In heavy buildings, all you can see a small gap will be there, the two buildings. Although it's a two places, there's no separation, everything, a small gap, very because it's for tolerances, that's what. And just allowance. Okay. Then for allowances, it is for a allowance for a specific variation in the size of a part is called dimensional tolerance, and allowance for a specific way for a specific variation geometry of the part is called geometrical tolerance. Then tolerances are used to control the amount of variation. It is mainly used to control the required how much amount of variation has to be can be inherited or can be accumulated or can be accepted in all manufactured parts. That's what. The tolerances are used to control the amount of variation inherent and accepted. It can accept or it can maintain or it can achieve or it can, what we can say, it can absorb or it can function the process even though that much amount of allowances, tolerances are. That's what tolerances are used to control the amount of variation inherent in all manufactured parts. That's what say. Okay, in all manufactured parts. That's what happens. Then you see, one of the great advantages of using tolerance is that it allows for interchangeable parts, thus permitting the replacement of individual parts. That's what happens. So one of the great advantages of using tolerance is that it always allows the interchangeability of parts, and by permitting the replacement of individual parts, that is, we have an option for we have an option for interchangeable parts. That is, we can have parts universally made so that it can be used for various other purposes. Although specification everything is same, we can use it for the same purposes. I can say an example like, okay, I can say an example. I will say about automobile. As we are mechanical engineers, we will be more interested in automobiles. So automatically in the case of automobiles, you have seen all the vehicles. Okay, for example, I'll say I'll just name a name, Maruti Suzuki. Okay, Maruti Suzuki, but it has got a 1.2 liter Kappa engine on, sorry, 1.1 Swift, Desire, everything it has been used. Okay, so multiple, the same engine can be used for multiple devices and it is having the same. So the parts can be also interchanged. So what, it is globally made and the production cost, everything is less, and comparatively it has got an allowable tolerance. So what, it can be used for a variety of purpose, or variety of products can be manufactured with the same material. That's what happens. So one of the great advantages of using tolerance is that it allows for interchangeable parts, thus permitting the replacement of individual parts. Okay, this mainly permitting the replacement of individual parts. This is what happens. So these are the main aspects of tolerances which I have discussed. So that's what we say. Like what, it is a available deviation of definition. Its amount of dimension may vary, and with respect to upper limit and lower limit, there are two dimensions of tolerances. That's one is dimension, and one is geometrical. One is regarding the size of the part. The second one is regarding the geometry of the part. Another one is the variations inherent to all manufactured parts. This is what happens. Then one of the great advantages of using tolerance is that it allows for interchangeable parts, thus permitting the replacement of individual parts. This is what happens. Okay. Then tolerances in relation to cost. Okay. Now we can say that regarding the cost effective of tolerance and allowances. Okay. Regarding the cost effective of tolerances and allowances. Okay. Now first one is regarding the cost. Okay. Now we are going to start with the cost. So tolerances in cost and this thing. What happens is like cost generally increases with smaller tolerances. So as the precision, we have discussed in the last class, as the precision and accuracy increases, automatically what happens is the products, okay, automatically the products, focus on the products will be increased. So when we are increasing the focus on the products, automatically what happens, more complicated manufacturing more complicated manufacturing machines and highly skills are required. So automatically the production cost will be high. So automatically what happens, when the production cost is high, automatically the cost of the product also drastically increases. That's what we say. Okay. So that's what. So cost generally increases with smaller tolerance, and small tolerance causes an exceptional increase in cost. Therefore, your duty as an engineer is to have to consider, do you need at a range of 1.0001 centimeter or 1.01 centimeters good enough. That's what we say. We have seen yesterday the same value in our vernier and screw gauge, everything. And already in the, while doing the labs, we are seeing the measuring instruments. It will be having a least count of maximum 1.01, 1.02. So it is the best way to measure the precision and accuracy. Unless it is not done, what happens, the product will be not for a specific use. That's what happens. So cost generally increases the smaller tolerance, and small tolerances may cause an exceptional increase in the cost. Therefore, as an engineer, as you after finishing you are becoming an engineer, you will become a quality control engineer. Okay, so all this comes under the process of mainly the quality control. We can say quality control, QC check. You can do. We have seen the sticker in so many purpose, so many heavy, highly priced components. Like in automobiles, you can see in the new vehicle there will be the side of the windshield, you'll see the QC okay. That is QC check. That's a quality engineer or quality inspection engineer who plays important the clothes, especially the clothes. You can see surplus. They say surplus or outdated clothes or surplus clothes or quality checked inspection failed code. That means it might be having a small twine or a small stitching. It's not a stitching, maybe not an order, a small disorder, but it will be not sent for the actual product. It will be removed. It will be discarded. Like it will be removed. So what happens is it will become a second quality product, but it is not. It is also the same brand cloth. Everything. What happens due to it is the company says we cannot sell that product, and it is being sold for scrap. That comes for a second quality material, and we might be getting it. So that's it. So all this aspect comes into the base of the various tolerances and allowances in the case. So I'm telling the variety of examples. So in a car, in automobile, we are saying in the car, and also in a cloth material. So this comes not only in this two, or it comes in a variety of products. Okay, that's what. So the cost generally increases with smaller tolerances. The smaller tolerances cause an exceptional increase in cost. So when I am giving an example, you study like that, so you'll never forget the basic concept of this. That's what I'm trying to do. So the smaller tolerances cause exceptional increase in cost, and therefore duty of engineer is to have to consider. Then do your lead and 1.001 centimeter or 1.01. That's what I told. Then parts with small tolerances offer require special methods of manufacturing. So according to the new inspection techniques or new inspection type of materials will be found out to have better precision, and accuracy, which comes to tolerances and allowances. Then parts with smaller tolerances often require greater inspection and call for rejection of parts. Greater quality inspection, greater cost. This is what happens. Vice versa. Okay, vice versa happens. Like parts with small tolerances. So mainly the parts with small tolerances or small dimensions. Okay, parts with mainly small tolerances or small dimensions. What happens? Because greater inspection. It always require mainly greater inspection and call for the rejection of parts. Then greater quality inspection, greater cost may also achieve. Greater quality inspection and greater cost also achieve. Then do not specify a small tolerance that is necessary. Okay, if it is small tolerances that is then necessary. Okay, do not specify. We need not specify small tolerance than necessary. That's what happens. This is what happens in the case of tolerances with related to the cost. Okay. Then dimensional tolerance representation. Okay. This is a figure you can see. The dimensional, this one comes to the directional limits and then comes to the tolerance limits. You can see. So this is a figure regarding the dimensional tolerances. Okay, this is the figure regarding the dimensional tolerances. So in the case of dimensional tolerances, we have the two aspects. Like see, one is the direct limit, second one is the tolerance values. Okay, second one is the tolerance value. So everyone just draw this figure regarding this is a simple figure, right? Just draw it. I'll give you I'll give you 2 minutes of time. Just draw it. You can write the name as dimensional tolerance representation itself. Okay, just draw the figure. Rahul, you have drawn the figure?
Yes, sir.
Complete. Fine. So you got the dimensional tolerance representation. You can see the minimum spacing. Okay. See, this is the type tolerance values. Like see, the 4 is there, but plus or minus 0.003. That is the limit. Okay. So this is 1 by 6 minimum spacing. That is 3.49 to 3.53. That is 0.449 means 5.50 51 52 53 0.04 is the tolerance. Okay, over there the diet limits is maximum 0.04 and the case of tolerance value it is only 0.003. So that is the representation of tolerances where you can achieve, although there's a small tolerance, but still what happens is there is no much differences. For example, you see here, okay, here in the case of here, what we are saying is dimensional tolerance representation. Like you see 22, but plus or minus 0.3, and here it is 12 plus or minus 0. There's a plus tolerance on top, and this is plus tolerance on top C plus 0.1 minus 0.02. So these are the various tolerance representation. Okay, these are the various tolerance representation where we can see these are the various tolerance representation. This is what happens. So the previous slide we are talking about dimensional tolerance representing what is tolerance. Then we are going having dimensional tolerance represent how do we represent the various dimensional tolerance. So in the case of direct limits, this is the way we represent, and the case of tolerance, normal tolerance values, we represent the same way. And now in the case of you see top on everything dimensional tolerances, see this is two types: unilateral tolerancing and bilateral tolerancing. Okay, this one is called unilateral and this is called bilateral tolerancing. So these are the various representations of tolerancing which always comes in just plus or minus 0.1 to 0.3. These are various types of tolerancing. Then comes the important terms. Okay, then comes the important terms of tolerancing. Okay, Then comes the important terms of tolerance. Hope so. You are seeing the figure where we can see the important terms of tolerance. Okay, important terms of tolerance. This one. So in the case of important terms of tolerance is, see, these are the main figures. So shaft, hole, everything. So come first we will shaft of the shaft. Okay, this is the shaft. Important terms in the case of tolerancing. Okay, we can start with the name called shaft. Okay, shaft. So a term used by convention to designate all external features of a part, including those which are not cylindrical. So just note down. You need not draw the figure in the note. You just note down. Okay, if possible, draw the figure also. The important terms we will be discussing about the shaft, then the hole, then basic size, actual size, zero line, limits of size, maximum limits of size, okay, minimum limits of size, allowance, tolerance, all this we'll be discussing. Then tolerance zone, upper deviation, lower deviation, okay, all this. Now, so all this comes will be representing in that figure. So you just while you need not write a definition, you can just note down the important terms and tolerancing and just note down the name. And if possible, you can draw the figure also. So you will have an idea. Okay, all those slides will be shared. My videos will be recording. But the important terms in tolerancing is first one is shaft. So, but shaft you can see the figure over here. It is a shaft over here. Where the shaft, a term is used by convention to designate all external features of a part, including those which are not cylindrical. That's what happens in the case of a shaft. In the case of a shaft, a term, it's mainly a term used by convention to designate. It is a term used by convention. All external features of a part, including those which are not cylindrical, including those which are not cylindrical. Alle. It might not be cylindrical also, but here we are drawn a shaft which is of a cylindrical. That's what. Okay, the presentation is given as a cylindrical. Okay, then in this you can see this is the basic size. You see this is the basic size and of the hole. Then minimum diameter, maximum diameter, all that. The second one is the hole. You see the hole here. We are representing the hole. See the on cursor hole. So what's hole? A term used by the convention to designate all internal features of a part, including those which are not cylindrical. So first one is a shaft to an extent of a part is named as a hole. In both cases, it should not be cylindrical, but here we are just giving a cylindrical representation. Okay, then so I hope so you have cleared the shaft and the hole in the case of tolerancing. Then comes just no, that's why I told just to draw the figure. Then comes the basic size. Okay, basic size. So in the case of the basic sizes, it is the nominal diameter of the shaft or bolt. See, this is the basic size. See, this is the basic size where we have the nominal. Okay, we have the nominal diameter of the shaft or bolt and the hole. But this is in general the same for both the components. Okay, this is in general the same for both the components. That's what happens in the case of important terms in tolerancing, where we have a basic size. So I am showing the figure where you can see the basic size. So this is represented as the basic size. So we have a basic size where the nominal diameter of the shaft or bolt and the hole is general for all the components. Then we name it the actual size. Okay, the measured size of the finished part after machining. That's named as actual size. Okay, that is named as the actual size. So this is the actual sizes. You can say this is not a finished part. We can have the finished part that we can say the actual size. Okay, that is the actual size. So here we have only the basic size. So it is a finished part. Always the finished part we can say the actual size. That is the part which is produced as per the requirement. The measured size of the finished part after machining. The measured size after the finished part after every process is over. Then we have the zero line. Okay, then we have the what we can say, then we have the zero line or what happens, zero line or line of zero deviation. This is the zero line or the exact point where we don't have any deviation or nothing is been done. That's one name, the zero line or zero deviation. So in the case of zero line or zero deviation, it is a straight line. Okay, it is a straight line corresponding to the basic size. Okay, it is the straight line corresponding to the basic size where the deviations are measured from this line. So this is the line which is the basic line. From this only we can calculate the tolerance and the deviations occurred in the product after machining or before machining or any time of machining. Okay, so that's named as a zero line where it is a straight line corresponding to the basic size. It is always corresponding to the basic size where the deviations are measured from this line, where in this case the deviations are measured from this line. Then the positive and negative deviations are shown above and below the zero line respectively, above or below the zero line respectively. Then limits of size, then comes the limits of size. So I hope so you have seen the zero line over here. Okay, and this is the zero line. Okay, zero line or zero line or zero deviation. Okay, that's what happens. Then we have then we have the limits of size. Okay, in the case of limits of size, the term limits of size referred to the two extremely permissible sizes for the dimension, that's a hole or shaft between the actual size should be lie. That is the limits of size, the term limits of size referred to the, just look on the figure or think about the figure and just look what we are saying. The term limits of size refer to the two extreme permissible size. That is the lower and the upper. Right? That's the two extreme permissible sizes of for a dimension of a part, hole or shaft between which the actual size should be. That is, it should be inside that the actual size. Okay, maximum it can be to that extent, or it should lie inside the both. That's what happens. The dimension should lie only then the product which is manufactured can be used for the proper function. That's what we say in the case of limits of size. That is the term limits of size refer to the two extreme permissible sizes for a dimension of a part in the case of a hole or shaft between which the actual size should lie, between which the actual size should lie. Then the maximum limit of size, what you can say the maximum limit of size, the greater of the two limits of the size of part, hole or shaft, that's what happens. The maximum limit of size. So the greater of the two limits of size of a part, the hole or shaft. That's what the maximum limit of size. It has to have the greater of the two limits of a size of a part, hole or shaft. That's what happens in the case of maximum limit of size. Then comes the, when we say the limit of size, it is between the two dimensions. Then becomes the maximum limit, the size of the two limits, the size of hole or shaft. The greater of the two limits. If it's maximum, this means the minimum is to be the smaller of the two limits, the same, the smaller of the zone. Is the greater, then this is the smaller. That's what happens. The minimum limit of size. The maximum limit of size is the greater, and the minimum limit of size is the smaller. See, maximum limit, the maximum, and this is the minimum. Minimum is the minimum. So this is the difference. Okay, you can see maximum and minimum. Okay, where the part should be. That's what we say after machining. Okay, sorry. So yeah, maximum and minimum. Then we have the allowances. Okay, allowance. It is the difference between the basic dimensions of the mating parts. It's always the difference between the basic dimension. So I hope so you remember. How do we get the basic dimension? How do we calculate all this? Can any one of you say? How do we calculate all this? For this we have a term. Can any one of you say? What is the term? Should I call the name? Or any one of can you say? Amit, can you say the line? For all this, measuring the elements, everything, we have a line. What was the line named? Rahul, would you say? Amit, yeah, come on, you can tell. Okay. Rahul, can you say? Do you have an idea? We have discussed.
Sir,
What?
tolerance.
No, no, no. Tolerance, Allah. Tolerance. For identifying tolerance elements, everything we have a line in this figure. We have measured the figure.
Zero lane.
That's what. Who has told? Rahul. Yeah, that's what. Zero line. That's it. Okay. So that's the zero line. See, this is the, we have told zero line itself. Okay. See, this is the basic line. I'll show in the figure. This is zero line or line or zero deviation. Okay. We have discussed that's the basic thing. See, it is a straight line corresponding to the basic size where the deviations are measured from this line and the positive and negative deviations are shown above and below the zero line respectively. So for all this allowance, tolerance, everything, the zero line place. So it is the difference between the basic dimensions. Okay, it is the difference between the basic dimensions of the mating parts, where when the shaft size is less than the hole size, and then the allowance is positive, and when the shaft size is greater than the hole size, then the allowance is negative. So this is what happens in the case of allowances. So it is the difference. It is always the difference between the basic dimensions of the mating parts, where the shaft size is less than the hole size, then the allowance is positive, and the shaft size is greater than the hole size, then the allowance is negative. Remember that. So if it is great, if the shaft size is less than the hole size, then it is called positive allowance, and if the hole end is greater, then it is called negative allowance. So this is what happens in the case of allowance. Then we come to tolerance. So it is a difference between the upper limit and the lower limit of the dimensions. We can see a basic representation of this figure. It is a difference between the upper limit and the lower limit. Okay, it's a difference between the upper limit and the lower limit. So see, it is between the upper limit and the lower limit of dimensions. Okay, so you can just okay, just note in the okay, absent. Agilem. Okay. Can you hear me? Rahul, am I audible, right?
Yes, sir.
Okay. So Agash K is absent, Agil M is absent, Amit K.
Yes, sir.
Present, sir.
Sir,
Okay.
Akash present, sir.
Where were you when you were asking the attendance?
Sir, then back sir.
Okay.
ഇതിലില്ലേ?
Fine. Agil M.
Sir, present, sir.
Agil M, where were you when you were calling?
Sir, ഇവിടെ നെറ്റ് ഇതായിട്ടാ.
Amit K. No, Amit is told.
Yes, sir.
Andrew Suresh,
Yes, sir.
Karthik Koteri,
Present, sir.
Ladin, Reza,
Present, sir.
Mobatism,
Present, sir.
Asaf,
Present, sir.
Fardeen,
Present, sir.
Fateh,
Present, sir.
Sama, Sian,
Present, sir.
Nisag, Nived Kumar.
Present, sir.
Nisag was present. Nisag? Okay, absent. Pratyush Premraj?
Present, sir.
Hope so you're fine now. You're okay, le?
Sir, okay.
Rahul Rajiv?
Present, sir.
Sarun Rajiv?
Present, sir.
Sauravar?
Present, sir.
Saurav Srijit?
Present, sir.
Srirag Vijayan?
Present, sir.
Vishnu AP?
Present, sir.
Vishnu N?
Present, sir.
Adarsh Manohar? Adarsh Manohar? Okay, fine. So, hope so you have drawn the figure. So now we'll just finish it by telling this important terms in tolerancing, that's it, and allowances, so that portion will be completed. So then we can have a tolerance zone. Okay, then we will be having a tolerance zone. So this is the tolerance zone where we say, okay, this is the tolerance zone. It is a zone between the maximum and minimum limit size. Okay, it is the zone between the maximum and minimum limit size. That's what happens. It's a zone between the maximum and minimum limit size. Okay, and in the case of this, the tolerance zone is the zone. This means the zone between the maximum and minimum limit size, and the upper deviation we have already discussed. It is the algebraic difference between the maximum size and the basic area. Okay, basic size. Okay, upper deviation. It's algebraic difference between the maximum size and the basic size. That we have to, and we have drawn the figure in the first figure, the previous slide from here. I hope so you remember upper deviation. See, okay, this is the upper deviation and the lower limit. That's it. But we are here name it as upper limit and lower limit. That's all. So upper deviation is this, where we have upper deviation is algebraic difference between the maximum size and the basic size, and the upper deviation of a hole is represented by a symbol ES, that is Eckhart Tolle, and the shaft and of a shaft is represented by ES. And the lower deviation of the algebraic difference between the minimum size and the basic size. So it is the algebraic difference between the minimum size and the basic size. It is here maximum size and basic size. Here maximum size and here maximum size and basic size, and here we have a what we can say difference between the minimum size and basic size. So the lower deviation of a hole is represented by a symbol. Here it was ES because it is upper deviation. We call it telescope. Here we have cut inferior and and of a shaft is represented by EI. This is what happens in the case of low upper and lower deviation, solid deviation. Now we are having a small example. Okay, we are having a small example where you can see the upper limit and the lower limit. So this is what, so engineering dimensional drawing. Okay, in the case of engineering dimensional drawing, this is how. So this is going, this small shaft can be mated over this part. So here what happens is, you see, upper limit is 49.7 and lower limit is 49.5. So there's a small allowance and everything kept so that it can smoothly insert inside this. And here also, see, upper limit is 50.02 and lower limit is 49.8. So what happens? This can easily come and enter this one. So see, this is the machine part. Okay, see, this is the machine part. Actual dimension measured is 50.1. Okay, actual dimension is 50.1. So now this is the part. Okay, this is the part which you are going to enter. So here we have what we have, tolerance of 0.002 and clear for 0.04. So maximum is 0.7. See, here we have a maximum of 0.007, an average of 0.004 and a minimum of 0.001. So this gives an example, tolerancing example. Okay, so I suggest you to just copy down this figure, although it will be available. Okay, just copy down this figure so that, okay, by giving a tolerancing example to have a basic idea. Okay, by this we can end our class. You can just copy that on the figure and complete it. Just name it as tolerancing example, but make it as 1 and 2. Okay, this one as an engineering dimension drawing and machine part. When it is over, just let me know it is completed. We can stop the class. Okay, so we were discussing about the various aspects, the theory of mainly about the allowances and tolerances. Okay, to an extent it has been done. Okay, tolerances and allowances. So Rahul, when it is done, when the figure, when you have drawn the figure, just let me know. We shall wind up the class. Okay.
Yes, sir.
Actually, I'm not focusing on the figure. I am focusing on that dimensions. You see, to have an idea. Okay, mainly regarding the dimensions, upper limit, lower limit. That's what. Okay, maximum deviation, minimum deviation, lower deviation, upper deviation. That's what. Maximum, minimum deviations, all that. Completed?
Yes, sir.
Thank you.
Thank you, sir.